Oh.
Maybe play from start.
Yeah, I'll try that. Is that, are you still seeing both?
Well, I'm still seeing your slide, but not in full screen.
How about that?
Same.
All right. I'll try one more thing.
Okay. Well, if
How's that?
okay, now it's in full screen. Yeah, it's perfect. That's
Yes, for some reason, the PDFs behave better than the PowerPoints with the Zoom.
yeah. Okay. Well, okay. I think everything is working. Thomas, I'm going to do a short introduction, and then I'll pass you the floor. Okay.
Yeah, that's good. Thanks.
Okay. Well. So. First, hello everyone, and welcome to another talk in our webinar series here at LIneA. Today we are starting a special series where we will learn much more about the LSST brokers. And there are several brokers that will work with the LSST feed. And today we have the pleasure of having Thomas Matheson from the NOAO. And today he will talk to us about the ANTARES, one of the approved brokers to the LSST. And also, before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or access it in our YouTube channel, LIneA MCTI. So, Thomas, thank you very much for being with us today. It's really a great pleasure, and the floor is yours.
Great, thank you. No, first, I want to thank you for giving me the opportunity to come and talk about the things we've been doing for time domain at the NOAR lab. So I want to talk about more than just the broker. The broker will be the focus of the talk, but I also want to give a little bit of an overview of some of the other things that we're doing for time domain at the NOAR lab. And just to make clear what NOAR lab is, I realize that the reorganization of the federal facilities in the United States is a fairly recent event. And so just to make clear how we're operating now, basically all of the ground-based OIR facilities that the National Science Foundation and the US funds have been organized under a single organization now. So that's all the elements of the Vera Rubin Observatory, the Gemini Observatory, and the elements of the former National Optical Astronomy Observatory, NOAO. So all those things that you've used to been seen as sort of as separate entities are now organized into one thing, which is the NOAR lab, which is the NSF's National Optical Infrared Astronomy Research Laboratory. And so all those elements make up the NOAR lab. The parts that were NOAO have been split into two components within the NOAR lab. One being the mid-scale observatories, that's essentially Kitt Peak, Cerro SOAR, all of the telescopes smaller than Gemini. And there's also the CSDC, the Community Science and Data Center, which is focused on things data related. So like the TAC, like our archive, like our science platforms. But more important for what we're going to talk about today, that's where the time domain services are based. So all of the things I'm going to be talking about today are developed within CSDC. But the advantage of now being within a larger organization that is one entity means that trying to bridge across all of these elements to provide a seamless way to do time domain astronomy, that's much more easy now than it used to be. So you can go from your proposal through getting alerts, through finding which alerts those are of interest to you, doing follow-up at our telescopes, doing the data reduction, doing the data analysis. All that is now going to be, can be under a single organization. So there's a smooth process through the whole thing. But the focus today is on our time domain services. And as we know, the time domain astronomy is changing really rapidly right now. 100 years ago, this was the state of the art where you used photographic plates, and photographic plates were great for time domain because you had an objective record of the sky at a specific time. And even more important, you could take another photographic plate and compare the two. And that's what's happening in this picture. That's Clyde Tombaugh looking at two different plates to try to find Pluto. And he looked at millions of objects on tens of thousands of plates to try to find that moving object. And even though this is about 100 years ago, you might think, well, plates were a long time ago. But some of you may know that we were still using photographic plates for time domain services for time domain surveys into the 1990s. So this isn't as long ago as it might seem. But there have been, serious advancements in how we do time domain astronomy. And one of those is that the technology for detectors has really helped us. So now that we use solid state detectors like CCDs, it's the same as a plate where you get an objective record of the sky at a certain point in time, and then you can compare that to a reference image where you can and the advantage of being a digital image is you can subtract one from the other, and that leaves everything that has changed. And in fact, you can automatically find all the things that have changed. You don't need a person to look at it anymore. You can have an algorithm look at the difference image and find things that have changed. And if you're really lucky, it'll put an arrow and point to the object for you, so you definitely won't miss it when you're looking at things. Now, once you have this ability to do this digital image extraction, it really opens up a whole new arena for time domain astronomy because you can find everything. And so now the question is, how big can you make your detector and your telescope to do this kind of detection? And so back in the year 2000, so 20 years ago or so, the Kate telescope was kind of a state-of-the-art way of doing time domain astronomy. And this was something my advisor built when I was in grad school. And back then we were lucky to get, a dozen supernovae a year or so. The number was so small that you knew each supernova individually. You knew each name, you knew what each one was like. And things have definitely changed since then. Now we have the Zwicky Transient Facility, which has a 47 square degree camera on the Schmidt telescope at Palomar. They're surveying essentially the entire available sky every night, and they're able to produce dozens of supernovae in a week. And coming soon, you'll have the Rubin Observatory's camera, where it's a little smaller field of view than ZTF, but because it's backed by an enormous telescope, that depth adds to the number of objects it's going to be able to discover. And so you get now dozens of supernovae every night. So we have exponential growth in terms of the ability to detect new and changing things on the sky. And this is happening right now that we've got this problem of how are we going to deal with this large volume of things that are coming? Here's another way of looking at the distribution of new time domain survey facilities. This is a figure made by Francisco Forster. So I assume when you have Aler come and tell you about their broker, he'll show you something similar to this. But you can see that there's been this huge growth, not only in the light collecting area of the telescopes that are doing time domain surveys, but also in the field of view that the instruments have, and also the number of pixels. It's just constantly growing at a rate that makes it very hard for individuals to keep up with the data flow that's coming from all of these facilities. But just having more a bigger facility and that allows you to go deeper and having a bigger camera to find more targets, it's not just that you find more of what you know. so far, whenever we've done new time domain surveys, it's opened up a new discovery space. So it's not just that you're finding more of what you know, you are also finding all the things you didn't know that were out there. So here's a diagram that Nancy Caswell put together a few years ago that tries to characterize transients. And you'll see that there's a time scale on the x-axis and a luminosity or an energy on the y-axis. And if you looked at this 20 years ago, the only things we really knew were the things in the gray boxes. So standard supernovae, classical novae. And everything else on there are objects that we have discovered since that time. And we've discovered them because we've had new kinds of time domain surveys that have explored new areas of parameter space in ways that we hadn't done before. So every time we try something new, we find things that we didn't know were out there. And in some cases, some of the elements, some of these objects are predicted, but for the most part, it's often a surprise to find all these new and different things. And we can expect that as these new surveys come online, like LSST, we will continue to explore new portions of this discovery space, find new and different things. And the key is going to be, how are we going to find it? How are we going to be able to distinguish new things from things that we know? And how are we going to find the things we know that we'd like to continue to study? And if you're like me, you've probably seen talks for the last 10 or 15 years about, oh, LSST is coming, LSST is coming. Well, as it turns out, if you look at this photograph of the telescope, they've actually built it. And the camera exists and the mirror exists. And so it's no longer a question of, well, at some time in the future, we are going to have to worry about what LSST is going to provide. LSST is going to turn on within the next 2 years, and we are going to start to get alerts from it. And when it does, with its 3.2 gigapixel camera, and its ability to survey thousands of square degrees on any given night, it will produce millions of alerts per night. And so it will become the greatest engine for time domain discovery that we've ever built for astronomy. And right now, we need to figure out how we're going to be prepared to deal with that issue. Now, often people refer to this stream of information flowing out of LSST as a fire hose of information. I actually think that sort of underestimates how it'll feel. I think it's really going to be like you're down here at the bottom of a dam with the water flowing at you. How do you deal with 10 million alerts a night? How do you find what you're looking for in this huge mass of information that's flowing out at a rate that and it never ceases. It comes all night long when you're having alerts after alerts after alerts. So it's an overwhelming problem for an individual astronomer to try to solve. And so that, in essence, is the problem. You have LSST that is going to produce on the order of 10 million time domain alerts every night for 10 years. That's 3,000 nights of 10 million alerts every night. It's an overwhelming number to think about how you would actually sort through that. In addition, most of these alerts will have fairly minimal information. There'll be a little bit of history for things that are repeating, but often it'll just be, there's an object at this place on the sky, and it's this bright, and maybe you might know how bright it was before, and that's about it. So it's not really enough to make an objective decision about whether or not you should follow it up. The other thing is that most of these will be known variable stars or moving objects. Every time a variable star gets hit, it will generate an alert, even if we know it's a variable star. And so this isn't to say that variable stars and moving objects aren't important. They certainly are, and we want to be able to track what's happening with them. But we also need to worry about the things that are rare and short-lived and require a more rapid response. And so we need to know all the things about the known variable stars and moving objects in order to understand how to provide those to people who are interested in those objects. But we also need to be able to identify those so we can see the things that are new and rare and need to be followed up immediately. LSST will find so many that a 1 in a billion event is actually a fairly common thing that it will discover. And so being able to make sure that we find those hidden rare things is really important for how we process the LSST alert stream. If you miss it, it's not going to come around again anytime soon. And so we definitely don't want to make a mistake and not be able to find those rare things when they turn up. The other thing is that in order to actually know when you found something new, just LSST detecting it isn't going to be enough. Until you actually have a light curve, a set of light curves in many colors, spectra, until you have all that kind of follow-up information, you don't really know what something is. You haven't discovered it until you know what it is. Just the fact that LSST detects it isn't enough. So we need to actually do more to understand what we've discovered or what LSST has detected to turn it into a discovery. And as you may have noticed, while there's been exponential growth in the ability to generate time domain alerts, the worldwide time domain follow-up capacity is not keeping up with that. We don't have growth in the number of telescopes that we can use to follow these objects spectroscopically or photometrically. So we are not going to be able to look at every object. We're going to have to think about how we filter through that stream, and then how do we use the resources available in the best possible way. And so we need a system that will sort and filter the alerts to enable this efficient follow-up. But we also need systems to make the follow-up systems we have now smarter and more efficient, so that we are better able to handle the vast new stream of alerts that are going to be coming from LSST. So the answer that we've provided for this, at least for the filtering of the alerts, is ANTARES, which is a software infrastructure system designed to process alerts at the scale that LSST will produce. We were initially funded by a grant from the National Science Foundation, an INSPIRE grant that was a multidisciplinary grant combining astronomy and computer science. And we've also received some funding from the Heising-Simons Foundation in order to continue development of the project. It's mainly been an effort by scientists and software engineers at the NOAA lab, but we've also had a lot of involvement from computer scientists at the University of Arizona. And we're also getting involvement now from some of the scientists at Space Telescope Science Institute, and also from NCSA, because several of our former team members have gone on to work at the University of Illinois. And so that's another place where we're doing some work to build the system. What we want from this is a tool that enables a broad scientific use of time domain alerts. We aren't trying to do any specific processing. We want to build a platform, a generic time domain platform that lets the user decide how they want the data to be processed and filtered. So right now, what we have is a system that allows anyone with an algorithm that can be turned into a filter, essentially a bit of Python code that I'll show later. If you have that algorithm that can identify the thing you are interested in, we can implement it right now. Now, I put an asterisk next to implement it, because if you give us something that is infinitely complex, then we'd need to talk to you about how we'd actually implement that, or if you want to rebroadcast the whole stream or something like that. But the point is that we have a system right now where if you have an idea, we can put it to work and start filtering alerts and give you the things that you're interested in directly to your own machine right now. And the system that we've designed is capable of handling the full LSST stream. We do real-time processing of the alerts. So on the order of minutes from the time we receive it from the telescope that's producing it, we have run it through our system and done the characterization that we do. We don't have any user restrictions on our data. Anybody can use our system. Anybody can take the data from our system. If we run into resource conflicts, we will set up the equivalent of a SAC to do any kind of resolution of those conflicts if there's issues with bandwidth or something like that. But for now, that isn't an issue, and we are certainly happy to have anybody anywhere use our system to do their time domain science. Recently, we went through the selection process with Rubin Observatory to be selected as one of the official LSST brokers. Almost all the brokers who've been working in this seriously have been selected as official brokers because they realized the bandwidth concerns weren't as great. And I'm sure you'll hear from some of the other brokers about what they're doing as well. Right now, we're actively processing the ZTF public alerts. The website here tells you where you can go to look at our portal to see exactly what's going on with our system. And if you're interested in more details, we had a paper published earlier this year that describes the system and some of the technical aspects of how it works. So we see the broker as being an element of the time domain ecosystem. And you need lots of different parts to make the ecosystem work properly. And so we've tried to focus on very specific elements for the broker. That's what we're going to do. And there are things that we are definitely not going to do. So in the ecosystem, you'll see at the top of this figure, we have the alert generators who produce the alerts. That flows down into the brokers that process the alerts. That information can flow to second level brokers where they can do more detailed or extensive analysis, but it can also flow to other software systems for automated scheduling of telescopes, for astronomers to look at the data and decide whether that's something of interest to them, or things can go automatically to telescopes and generate follow-up that way. But because we are trying to make sure that we don't have our software system grow into something that is bigger than we can handle, we definitely have put this box around it about what we want to do. So for example, we are not going to do the image differencing. We are not going to identify the sources on the images or assess the validity of those sources. That is all something that the alert generators have to do, mainly because the people who have built and are working with the cameras know them the best. And so they should be the ones to decide, how do we determine whether or not we've identified something, what's a valid object, and then they send that out to us. We also don't identify new moving objects. That requires your ability to track the object across multiple images. And the way our system is designed is we treat alerts as independent events. So we aren't going to do that. Fortunately, that is an on-project task for LSST. So they are going to identify the new moving objects in their own system. Known moving objects are flagged, so we can process those. And then for the things downstream from us, we don't want to do anything about coordinating follow-up. We are not going to tell you which target to follow. We are not going to tell you how to follow it up. That is something that needs to happen by individual astronomers and science teams taking the data that we provided them, and then you can decide how you want to act on the information that we have given you about these time domain alerts. So that's a lot about what we don't do. What do we do? Well, we annotate the alerts. That means we add value to the alerts from external information that we know about that position on the sky. We then use that information, either the information that comes about the alert itself, in addition to the annotations that we've provided, we use that information to characterize them. That's where the filters come to place. They use that information to make decisions about what something might be. We can rank that in terms of how much faith we have in any of those characterizations. We store all of this information along with the value added information on the alerts in an archive, so it's accessible after the fact. And then we distribute these alerts, and it can be distributed in a very fine-tuned way so that you only get a specific subset of the alerts that is of interest to you. So just to give you an overview of the technology, this is probably more information than you want to know, but I just wanted to give you some idea of how the system works. The overall system is a Kubernetes-based deployment. Kubernetes is a container orchestration system. Essentially what that means is we can take the software system and deploy it on any kind of data platform. So we were running on a series of machines in our own facility here in Tucson, and we've recently moved onto the Google Cloud platform. But having it be containerized like this means that it's a flexible system that we can move from place to place easily. To move data around, we use a Kafka streaming technology. This is an industry standard for moving data around the web. This is how ZTF transmits its alerts out. It's likely how LSST will transmit its alerts out. And it's a very simple way of moving data around. And for people who use our system, we've built a Python client that makes this very easy to do on your own machine. We use Cassandra and Elasticsearch database systems. Cassandra is a NoSQL system. We've learned that to scale to LSST rates and eventually the petabyte size of the database, that we need a different kind of database, and Cassandra has turned out to work fairly well for us. It's fairly similar to the database design that Google itself uses for their internal databases. Throughout all of this, we track the provenance of the alert processing, so we know exactly what has happened to make a decision. So all that information is available to you. You know how that works. Like I mentioned, we've now deployed to the Google Cloud platform. The other thing, this is all open source software. So if you go to that GitLab address at the bottom of the slide, you can see all the code that we've got. So it's all open. You can see exactly how everything works and how we're doing this. So the point of this is just to make it clear that we are using mature standard technologies to build the system. It's very stable. These are supported platforms that we anticipate being usable throughout the lifetime of the LSST survey. And so we are very confident in the stability and operability of the system. So how does Antares actually work on alerts? When alerts flow in, we initially annotate that with information from multi-wavelength catalogs. So we say, once we know the position, we can go query all those catalogs. We keep the catalogs inside our system. We don't query out to to the catalogs that are stored elsewhere on the internet, just because the latency to do that is too great. So we keep all the information local, and we do these associations across these multi-wavelength catalogs. These catalogs are everything that you might expect: Sloan, Gaia, WISE, Chandra, all the things that you might find useful information that would help you to understand or characterize the object that's happened either near that or on that, in that object. We then take all that information and operate filters on them to make decisions about characterization. All that information is stored in a searchable archive, so you can get all this information out after the fact. We also provide watch lists. These are ways where you can upload a list of your favorite targets. So if you have a star or some object that you think is really interesting and you want to know if something is happening, well, you can upload that list of those targets to us. And then whenever an alert happens on it, you can get notified directly. We do this via a Slack channel, and so you can make it as intrusive as you want to wake you up in the night if you want that an alert has happened on your object. And so you can go ahead and add one of those right now, follow any object that you want. All this is available through our web portal, where you can see the streams that we do. You can look at the filters, you can look at light curves. All this information is available on the web portal, and I'll show some more of that later. And the other thing is that the tool we have has direct integration with other software systems that enable downstream follow-up. So like I said, we're not coordinating that, but we're making sure that we provide information to these downstream tools that people can then use to either try to understand what it is that they're looking at in the data, or they can use them to immediately generate follow-up observations on various telescopes. And so I'll talk more about these target and observation managers and EON, which is a telescope coordination system that we at NOAA Lab are working on. Just to give you some example of the filters, because the filters are really the key thing about how you as a user can interact with the system. The filters can be very simple. It could just be, am I near a known extragalactic object? So am I near a galaxy, and what kind of galaxy? That's a very simple thing to do. Am I in Andromeda? Am I a nuclear transient? Am I a known solar system object? So there are very simple ways of doing things that, that you can write filters. So it can be that easy. We also have contributed user catalogs. We have a catalog of known of galaxies that are more likely to host tidal disruption events. And so we can say, well, I might be associated with that, and I'm a nuclear transient. So you can have multiple characterizations that combine in a filter to make a decision like that. We also have filters that can deal with large area discoveries like gravitational wave counterparts. As soon as a LIGO event is issued, we can generate a filter automatically and start reporting immediately any alerts that happen within that footprint. And you can also use other aspects of the filtering to try to characterize any object that is found within that footprint, to try to say, is this a kilonova? Is it not? What are the interesting things I'm looking for within that footprint? Finally, we can adopt filters that are very complex. For example, there's the AstroRapid light curve classification tool. This is a machine learning based light curve classification system. And we can implement something as complex as that as a filter in our system right now without any trouble. So we can go from very simple to very complex. As long as we can implement it within the code within our system, we can make sure that your algorithm operates. So how do you get this information out? Well, these alerts that have been annotated and filtered, we use the feature calculation to make ideas about what they might be, and the matches. All this stuff comes out in the alert and the filter processing. So all of that is added to the alert that then you can look at. And the output comes out in 3 different ways. You can look at our web portal, but there's also a programmatic interface to that if you want to do it automatically. There's the Slack channel where we're putting out the watch list alerts. And then there are the full Kafka streams. And this is where our system provides a real powerful way to look at the data. Essentially, you can write a filter that generates a stream of alerts. So it cuts out part of the whole stream, finds that subset of the stream that is of interest to you, and then you can have that directed automatically to your own machine, have the alerts just drop onto the disk on your machine automatically and be there for you to process in your own way. And like I said, we've written this Python API that is essentially just a client that you install this Python client on your machine. We give you a secret key to access our Kafka stream, and that's it. It automatically comes to your thing. So it's very straightforward to be able to have a stream of alerts come straight to you, a specific and customized stream come straight to you. And then there's the archive, of course, where you can look at things on a longer time scale. So here's a look at what the portal has. You can see the light curve, the whole history of it. We use an Aladdin light window, so you can look at various different surveys to see what older images of the field look like. And we provide links to some of the other brokers and to other external services to search there if you're interested in that. You'll see that we also list every single alert that's in that light curve down below. And so in fact, you can go click on one of those and you can see the individual information for each alert that we've received on that. So here you can see the magnitude that we got on that particular day and time for that object. Down below that, we have the catalog association. So here you can see I've opened up the assassin catalog match on this. And if you look down at the bottom, you can see that, oh, this is a known object in assassin with a period of about 300 days. So it's some kind of long period Myra-like object. But the point is that all this information that was not in the alert when we got it from the survey is now all collated into one place so you can see it easily and directly without having to do any extra querying yourself. And like I said, the filters are the main way people interact with it. And in fact, one of the unique things about the Antares broker is that you can write the filter and send it to us. It's in Python, so it's really straightforward to do. It has access to all those features. What you do is at the end of the Python code, you generate a tag that you add to the filter, and that tag can be like anything you want. I'm in M31, for example. That tag becomes a searchable element within our database, and it's what produces the custom output stream. These can be completely user designed. So if you go to the NOAR Lab Data Lab, there's a Jupyter-based development kit, and it will guide you through the whole process of how you can put together a filter, and then you send it to us, and we can run it. While in the testing stage here, when you're working on the data lab, you can pull over real alerts and test your filter right then to see what it does. And so here's an example of a filter that is running. This is the one that identifies things with high signal to noise ratio. So if you only want alerts where you're absolutely certain it's a real astrophysical event, as opposed to a more marginal detection, you could use something like this. And you can see that it's a fairly simple Python code that does this, and it generates a whole separate stream of high signal to noise ratio events. And the other thing is that it's fairly straightforward to do this. I mean, even I have written the filter, and I'm not the best Python coder in the world. So if I can do it, probably anybody can. So it's really easy to write your own thing right now and get your own data right out of our system. So as I said, there's these other software systems that go along with the broker that enable us to do a full system of time domain astronomy across the entire NOAR Lab set of facilities. One of those are things called target and observation managers. These are other software systems that live downstream of brokers that process, that allow users to process and collaborate on data. And the key thing about them is that they also have tools built into them to automatically generate observations and schedule them at a large range of different telescopes. The TOM toolkit, where this is started, is built by Las Cumbres, and lots of people have built these kind of software systems to manage their data. These are great ways to organize all the data that you're looking at. It allows you to collaborate in large teams and make decisions about individual objects. It allows you to query out to find out more about the data that you've got. It allows you to interact with different data systems within the observatory and to schedule observations on various different telescopes. We've taken that toolkit and put more specific Antares related things into it from our own version of it. And you can get the copy of our version of the tool of the TOM from the web address down below. This has built-in ways to do automatic querying of the database with all the alerts and to create observations for the telescope follow-up system that I'll get to in a minute. And you can do either very simple queries or complex queries. The point is that what we've got is a system that allows you to use the Antares database directly to find objects and then go and schedule observations on them. We also have this TOM can also be programmatically accessed, so you can create target information. You can pull out light curves with this software system, and you can also interact with the TNS system to try to interface, to try to get other data from that, so you can compare all the data in one place. And the web link down at the bottom of this page goes to a Jupyter notebook that illustrates ways of doing all of these things with this ANTARES specific TOM that we've built based on the Las Cumbres TOM toolkit. The next phase, or the next step in the software that would be used after you've used the broker and the TOM is this system called the Astronomical Event Observatory Network, or EON. This is another project where we're working with Las Cumbres Observatory to try to build a network of telescopes that have a common way of programmatically accessing them, scheduling observations, and making them dynamically scheduled so that these time domain events can be folded into the observation program easily and smoothly without too much disruption to the whole system. So we are slowly adding more facilities to this network. All you have to do is have something that can have an API that can accept these requests and can also let the system know what is happening at the telescope, and something that at the Q observation mode clearly is very useful for this. And we'd like to have systems that have easy access to the data and preferably reduced data. And so right now, the main focus has been to develop this with Las Cumbres and SOAR. And SOAR, in fact, has been the main test bed for what NOAR Lab is doing to try to build this network. So the main thing right now, like I said, is SOAR is the focus of this, but also Gemini in terms of making sure we can use these tools to automatically submit requests. SOAR itself has run as a separate telescope within the Las Cumbres network. So you could actually, on Q nights with SOAR, you could use the Las Cumbres scheduler to activate observations there. We've also been trying to build data pipelines and archives so that the data that is produced by telescopes that are part of EON provide not necessarily science quality reductions, but at least data reduced to the point where you can make rational decisions about whether or not the data you've got is of the highest quality to decide what you need to do with it, or enough information to be able to make a decision to go the next step after getting the reconnaissance spectrograph. And right now we're using the TAC process to try to encourage people to take more advantage of this EON facility that we're building. It's been operating at SOAR for a couple of years now within the NOAR Lab time, and people can request things directly through Las Cumbres. There's also an API through Las Cumbres, so you can request this, and essentially you can use one of those TOMs, those software systems, to say, I need an observation of this object with Goodman, and you can provide the setup in there, and it automatically sends all that information to SOAR where the observation is taken for you in the way you want it to be done automatically. We're already also working with this with Gemini. It can interact with Gemini through the existing APIs at Gemini, so you can automatically trigger observations. You can get information out of the observing database at Gemini, and you can get raw data out of the Gemini archive through through EON and the extensions they've built for the TOM toolkit. And in fact, you can actually take that information from a TOM, and it will directly create the observation in the tool at Gemini. So if you've ever tried to put a target of opportunity in at Gemini, you know how you have to go in and copy the observation and put in your target and all this other stuff that you have to do manually. With the TOM toolkit and Gemini's connection to it, you just have to say, create target, and it does all this automatically for you. It fills in the Gemini tool and then activates it so that you can get the observation right away. So I don't want to give you the idea that all we're doing is writing software. We are actually also using the ANTARES system right now to do actual science. The science that we have been talking about all along, the capabilities we said we could do with ANTARES, we are already doing it. So right now it has the capacity to produce these scientific results. So you can see this laundry list on the side of a whole bunch of ATELs that we put in, and then several other papers that we've published in the last couple of years that we've been able to actually really take advantage of that ZTF alert stream, use ANTARES to find interesting things in it automatically and rapidly in order to respond directly to them. And in fact, we have recently recently added the capability that we have automated reporting from these anomaly filters into the transient name server, the IAU supported way for identifying new transient objects. And I just want to highlight a couple of the cases. One is here we found the first R Corona Borealis star in the public ZTF stream. And here Antares flagged something because, oh, there's a drop in brightness. But we also had the catalog association from WISE to suggest that it was an infrared bright source, suggesting an R Core Borealis star. So as soon as we saw this, we got a spectrum that revealed, yes, that's what it was. So here's the whole story of how Antares can work. It finds something, alerts you to it, provides you with the contextual information to make a decision about it, the fact that it had the infrared excess, so it was likely to be this. And then you can act on it rapidly in order to get the spectrum and follow it up. Another example is this WZ SGE type dwarf nova, which is essentially just a rare type of dwarf nova. And we have an anomaly detection filter running in Antares. It looks for anything that might be unusual. And this triggered it, and we were able to respond rapidly to get a spectrum while it was in a state where we could definitely know exactly what kind of object it was. So, and then generate this whole series of follow-up photometry. Again, it's the whole idea that this provides you with a way of automatically getting a report of here's something strange and new that we need to react to right away. And so this is what Antares is already enabling for us. We are already able to do this, and we are prepared to continue to do it as we go to the next stage beyond just processing the ZTF alerts. So that's the big question is, are we sure we can actually do this at the LSST scale? And so you can see here this figure showing a test we did by operating in Google Cloud, processing ZTF alerts at the LSST scale. And this is showing that the processing time versus the length of the light curve is effectively a linear thing. That's a good thing because it means that it's not an intractable problem, but by the time you get to the end of the survey, that it's almost impossible to run in real time. Turns out we can do that. So we have load tested the entire system on the Google Cloud platform using ZTF alerts. On the cloud platform, that was really a big advantage for doing this kind of test, because in the cloud, you have the ability to flexibly add machines and scale things out to accommodate the greater volume of data that will come with LSST. And we were able to demonstrate that the Antares technical solution, the way we are operating right now, the database system that we're using, the pipeline system that we're using, all of the orchestration that we're doing, it all works at the LSST scale. So we are confident that we will be able to operate on LSST and within Google Cloud where we are right now. So we are really feel like we are in a good place, and that is not going to be an issue in terms of the ability to scale up to handle the volume of alerts that we will end up getting from that. So we are also working with other broker teams. I think you've already heard from David Trilling about the SNAPS broker earlier. We provide the stream of known solar system objects to them, and then they operate on those events to try to analyze them in the way that they are experts in doing. So it alleviates us from having to be a solar system broker, and by us peeling off that portion of the stream that contains known solar system objects, that means that they don't have to get the full stream. They only get the stream that is of interest to them. So we can carve out a piece and send it to them. They can process it. It makes it easier for everybody to be able to have the brokers specialized in this way. And we're also going to start working with the point of interest variables team at Vanderbilt to also provide them with a stream that they can operate on to do the interesting work they want to do on studying variables. One of the other groups that we're working with is at Purdue University, where they're trying to build a tool that will automatically recommend which targets need the follow-up next. And so this is a thing called the Recommender Engine for Intelligent Transient Tracking. You can go to that website to look at what they've been doing. And what they do is they carve out, like the solar system team, they carve out a special subset of the ZTF stream using Antares. They have various parameters that identify which objects are of interest to them. We operate on the stream. we narrow it down to that subset that they want, and then we send it to them. They then use that information to try to characterize the objects and say, okay, of all these objects that we've got, this one is the one where if we got an observation now, we would be able to learn more about it. And so they are trying to build a system that has that list of recommendations, and then they're going to have a network of follow-up telescopes that then operates on those recommendations in order to provide a better characterization of all those individual events. And so they actually have a huge network of amateur astronomers who are involved in this to try to help provide them with the data that they need to understand how to characterize these alerts better. And so this is an example of a tool that exists downstream of ANTARES that they would not be able to do on their own without us carving off the substream that then they use to try to identify targets of interest for them. So I hope I've shown you that the NOIR Lab, in addition to talking about ANTARES, but wanted to show that NOIR Lab as a whole, right now we are trying to build a comprehensive time domain system, from having a TAC that understands how time domain projects work and how the allocation has to work for that. We have Rubin Observatory, which will be the greatest alert generator the world has ever known. We have ANTARES to operate on those alerts. We have EON to take those alerts once we've processed them and people can have decided what they want to do follow-up. We have EON that will enable them to do follow-up across a network of telescopes where we're trying to add more, and part of the Rubin in-kind contributions will also contain telescopes that get added to that network. And then we have telescopes that you can use for the follow-up that can be automatically integrated into this whole system, Gemini, SOAR, and Blanco, where we're building tools to make them better at scheduling time domain observations, better at rapid response, and better at providing reduced data to you so you can make a decision rapidly without having to have multiple steps in your way. And then finally, we have the Astro Data Lab, which provides a science platform where you can do analysis on the objects and try to do further understanding of the data that you're looking at. And finally, I just want to end by showing this another picture of the portal, because I think no matter how much information I could convey about what ANTARES does in an hour or so, the best way to see what it can do is for you to go to this website and look at it and see what it does, and to start to play around with the tools that we have and to look at how to make a filter and do it yourself. And then you can actually see the power and capability that we are providing with this system. And I really encourage you to go look at it, see how it works, and then get in touch with us, because we are happy to help you to try to implement the tools that you want within our system so you can do the science that's of interest to you. That's our goal, is to make a platform that does time domain astronomy for the way that you want to use it, the users want to use it. That's our goal. So thanks again for your attention, and thanks for letting me talk about all the time domain astronomy at NOIR Lab. And I'd be happy to answer any questions about this.
Thank you, Thomas, for the very interesting talk. We now have time for questions. If you joined us on YouTube, you can put your question in the comment section.
Well, sorry.
Okay, go ahead.
Sorry. It's not a question, it's a comment and a compliment. Wow, I wish I were 20 years old starting my career now. That would have been very impressive. Congratulations, beautiful, the whole thing. I was at ESA when they started the observing block stuff with VLT, and everybody was so impressed that you could prepare observing blocks and everything. I mean, this is another level. Congratulations.
Okay. Well, it's a big team, and especially the ability.
Oh, I understand, but but the nice thing is the vision. I mean, God, it's just. I'm from the days of taking Polaroids to actually finding shots, so I do appreciate that. Congratulations.
So, thank you.
Thank you, Luis. More questions? Okay, Felipe, go ahead.
Hello. Thank you for the very nice talk, and indeed it's impressive work. So my question is about the watch list that we can create. Mm-hmm. So I understand it can be of solar system objects, right?
That's a good question. I'm not sure about that. I think that we can do solar system objects, but I need to check that for sure. I know that initially we didn't, but I think we got a request to add that capability and it should be in there now, but I'm not 100% certain. You should check on that.
So then the following question would be, what kind of filter can we implement? I'm thinking on the data. So the data would be, I mean, the filter would be on the magnitude, amplitude, variation, or color, or what?
Essentially, yeah, the filter can use any feature you want. Any of the information that's in the alert packet is accessible and you can use to make a decision. So, you know, the most common ones are, like you say, you know, the magnitude or color or things like that. But any of the information is available. You know, you could use things like, you know, is the ellipticity of the PSF to decide whether or not it's a moving object or something like that. All that information is accessible to you if you want to use it in addition to the catalog information. So that's all there. I'm now remembering better about the solar system objects that, in fact, what you might want to do is, instead of doing it as a watch list, is you want to do a filter that looks at the looks at the known solar system objects, and then you would operate on that to pull out the object that you want, the objects that you want. And then that would be a more straightforward way to do it, I think. But either way, I'm sure there's a way to do it.
Okay. So when it's observed, then we can pull out and take data.
And in fact, if you do it as a filter and create the stream, it's like you don't have to do anything. That data will appear on your machine automatically through this Kafka streaming tool. So yeah.
Well, I presume that's basically what Snaps is doing, right?
Yeah, no, Snaps is taking the full stream, and then they are looking for changes in brightness of these solar system objects compared to what is expected from their orbit and other things. So I think that's mainly what they're doing, but I'm not sure if you have specific things that you're looking at, it might be different than what Snaps is doing. It also may be that if you are looking specifically at that, it might be better to work within the Snaps system, but they don't have the same user filtering capability that we do.
Okay.
Yeah. But I know they're happy to work with people, so you know.
Well, David's scheduled to give a talk here too. So
okay, well, you should definitely listen to what David has to say. I should also mention I'm also part of their team, so I'm happy if you work with either group.
Okay, so you have a double head. Okay.
Right.
Julio, go ahead.
Hi. In one of your slides, you mentioned, I don't know, some integration or something, or combination with the tech processes.
Right. So what we're trying to do is to make sure that the TAC processes can handle time domain requests, because right now time domain is sort of treated as the same as any other kind of proposal. And in fact, it really needs to be treated a little differently because of how things are scheduled and the fact that you might want to move things from telescope to telescope as opposed to a static science case. So what we want to make sure is that the time is allocated in a way that is friendly to time domain astronomy. And part of that also means making sure that the telescope scheduling is friendly. And so to a certain extent, that's really just making sure that dynamic scheduling is something that all of our telescopes are capable of. And so like the example I gave was that Las Cumbres has provided us with a dynamic scheduler, and SOAR can be part of that. Not all the time, but it's part of it during certain runs where it opens the queue to that. The thing is to make sure that the TAC process can allow proposals that can take advantage of that. And so we don't want to build something that provides only a capability of the telescope, but nobody can apply for it because the TAC process prevents them from doing it. And so that's what I mean by we're trying to build this comprehensive system such that when you put in the proposal at the beginning, that's all you have to do. And then everything else happens more or less automatically with your input when you need to make a decision about which targets are of interest.
Okay. Thanks.
Mm-hmm.
Thank you, Julio. Let me also ask a question. So Antares does not provide, let's say, something that if I wanted to query directly from a Jupyter notebook, first I have to create a filter. That filter will create a stream.
Oh, no. And in fact, if you want to query directly to the database, you can do that either through the web portal or programmatically or through a Jupyter notebook. All those tools are available in our system to do querying. Yeah, so the database, you don't have to have a filter to have access to that. The database is there and accessible through all the standard ways you might want to access a database, right? So, and in fact, I think I showed the slide of the extensions we've added into this target and observation manager for Antares. That has a built-in element there where you could do a query directly from that, or you could do it from a notebook. There are a lot of easy ways to access it programmatically.
Okay, so for the user, what is the difference from this query to a stream generated by a filter?
Well, I guess the main difference is that the stream is sort of a real-time thing. So if you want to know now, that's how that gets to you. If you want to know after the fact, and so it sort of depends on the time scale of the events that you're worried about. You know, if you're worried about, if you're studying MIRAs, you probably don't need to know every time it alerts, but you might want to be able to look at all the MIRAs in the archive and then be able to extract those light curves and do the science you want to do with them. So it just depends on what targets you're interested in, how you'd interact with the system, whether it's long time scale or short time scale. And so I think it's more or less up to you how you want to get involved with it. That's one of the things we try to do, is to make sure that the system has that kind of flexibility so that it's easy for you to do what you want to do. We don't want to make it hard for you.
Okay, thanks. We still have a little time for questions. Okay, well, if there are no more questions, we will now wrap this up. Just some final remarks. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Anais Moeller from the Swinburne University of Technology, and she will give us a talk, an overview about the Think Broker. So thank you everyone for attending, and a special thanks to Thomas. Thank you, Thomas.
Thanks again for inviting me. I enjoyed talking with you.
Okay, thank you very much. Thank you everyone, and everyone have a great day. Stay safe, and I hope to see you all again next week.